So what's the goal of this talk? It's going to be a bit of a survey. Yeah. So I decided because I'm from a field that's adjacent to modular forms, but not, most of you will not be experts in this field at all. So I'll give you a little bit of survey what kind of modular forms appear, and I give a few of my own results. And that's why I have these two blackboards on the left side, and they will stay up during the whole talk. Yeah? And this is somehow, so when you have vertex algebras, and I will explain in a second what you can roughly think of when I say vertex algebra, this is just an example. So they're kind of complicated objects in representation theory, and when you study them, you often study not vertex algebras themselves, but you study some kind of shadows that they cast in certain directions. And they have maybe the three best understood shadows that they cast. You have their trace functions or characters. These are Q series in the easiest cases, and they usually become modular forms. And I'll explain this. So you have some number theoretic aspects. Then you have the representation categories. And in the best cases, they are modular tensor categories. So these also admit an action of SL to Z. So these are very nice categories. So we have this category aspects. And then finally, more recently, people have also tried to understand vertex algebras by reducing them to something geometric. I'll explain this. So we have these geometric, representation theoretic, and number theoretic shadows of vertex algebras. And it's from experience, and some of these are theorems, so a lot of these are conjectures, we see that the complexity somehow is parallel in these different areas. So when you have, so I call this A, B, C, and D, and I will explain in a second. When the associated variety of a VOA, so this is in general just an affine Poisson scheme or affine Poisson variety if you reduce it. When that is simple, then the representation theory tends to be simple, and also the characters tend to have nice properties. And when you increase the complexity somehow, or you reduce the assumptions, then also the representation theory and the characters become more complicated. And I will give you many examples. So that's the idea. I give you many examples of what's happening. Okay, so maybe let's go through this, and I will leave this, as I said, during the talk. So the nicest examples of vertex algebras that you can have, and this is what you had in the beginning of the story of monstrous moonshine and so on. So these are vertex algebras fit in this category A, in this family A. So there the associated variety is just a point, so there is no geometric datum. So it's completely boring from a geometric point of view. And the representation category is semi-simple, so every module is completely reducible. There are only finitely many irreducible modules, and all of these modules are ordinary. So you can have wild modules, but ordinary modules are exactly the one that admit characters. So the definition of a character is just take a trace over the module, and this is an infinite dimensional space, but it's graded, and this is the operator that grades it. So you can think of an energy grading. And you want these so this is then acting semi-simply for ordinary modules, and the eigenspaces will be finite dimensional. So this is just, of course, a Q series then. Right, so this is ordinary modules. For us, it just means it admits a character. So this thing is well defined. And L0 acts semi-simply. Okay. So you have finitely many of these irreducible modules, and you can write down their trace functions or characters. Characters is a stupid word, but we just, for historical reason, call them characters. So these trace functions, and then they don't need to be linearly independent, so they span some space. And you can prove, and this was done by Zhu in '96, that the space is invariant under the action of SL to Z of weight 0. So this is modular functions, but in a vector valued sense, and they're weakly holomorphic. So in general, to make this modular, you have to. I mean, often the energy grading starts at 0. But then to make this module, you have to subtract the central charge, and so this typically means you have negative Q exponents. So these will be holomorphic, so they converge to holomorphic. So you prove that they converge to holomorphic functions on the upper half plane, but you will have poles at the cusp, infinity. That typically happens. And you can even prove, this was done later, that is factors through gamma n. So the individual characters of the modules will be honest modular forms, weakly holomorphic modular forms for some gamma n. So this is the nicest case. That setting somehow we understand quite well. Then you can go to a somewhat weaker setting where the variety is still a point, but now we don't require the category to be semi-simple anymore, which means you will have reducible modules. You still have finitely many irreducible modules, and they are also, all of the irreducible ones are ordinary. But now, if you look at the space that's spanned by the characters, it will not close under SL2Z in general. So what you have to do to make this close, you have to add pseudo-tracers. So I'll not explain exactly how they are defined, but what you do is, instead of just looking at the irreducible modules, you also have to look at some certain reducible modules. And on these you can define pseudo-traces, and the thing that happens now is these pseudo-traces can have logarithms of Q, positive powers. So so this will be, so the characters of these pseudo-traces on these reducible modules then that you have, it's finitely many again, will be polynomials in log Q with coefficients, again, holomorphic functions on the upper plane. And that they collectively, again, in vector valued sense, under the Peterson slash operator of weight 0, close under SL2Z, right? But that now means that, of course, the individual components can be modular forms of mixed weight, can be quasi-modular, because you have these log Qs from other, if you apply the S transformation, you get the mixture of everything, and they will just appear from the other components, right? So that's why we see here in these cases, and I'll write down examples, modular forms of mixed weight, and this, but you should always think of everything transforming under weight 0. Yeah? Right. Then you can go away from this, and now we come to the point where you have something there's something geometric there. So you have a variety, and this is now, let's say, a nice symplectic variety. So if in general it's just going to be a Poisson, affine Poisson variety, but the Poisson bracket could be degenerate. So in particular, this has to be non-degenerate. Yeah, I'll stay a bit vague here. So there's a definition, and they're called quasi-Lis. Right, before they were called Lis, or yeah, so that's just the way they're called. So then you have these quasi-Lis ones. Again, the category will be not semi-simple. Now you don't necessarily have this property that all the irreducible modules are ordinary. So you will have modules that don't admit characters in that sense. So we have to kind of ignore them. But there will still only be finitely many irreducible and ordinary modules. And now what's probably going to be the case is if you restrict to those that admit characters, and again you add these pseudo-traces on these projective covers of these modules, you'll have something that closes under SL2Z. But that's just a conjecture, so that's not proved. But in examples we see that happening. I will say that you can also, for non-ordinary modules, sometimes write down Jacobi in a Jacobi sense function. So you need some other grading that comes maybe from, if you have maybe some SL2 action, you can take this H in the SL2 triple, and you give an additional grading, and maybe together with that, you have finite dimensional weight spaces, and then you would have modular forms in a Jacobi sense. Right, so that happens in some examples. And then if you go away from this, you make no assumption whatsoever, then your associate variety is just going to be some affine Poisson variety. Then you can have infinitely many irreducible and ordinary modules. So the space of characters already that span is infinite dimensional. Well, it's not clear what happens then, right? I will write down one example where you can then understand modularity in the kind of infinite dimensional sense. Other examples where you can see this, Katrin Pringmann and Anton Milasch are the ones studying this mostly. You see mock modular forms in the form of like higher rank partial false theta functions. Right, so then, but there we have no good understanding of what can happen in general. Okay, that's the overview. Yeah? Now I was not going to define vertex algebras, but I decided maybe I give you a rough idea. Let's start here in the bottom right, and this is also going to be basically these things that are called associated varieties. So if you start with something, and we want to have a symplectic structure, so the easiest symplectic vector space is just you take a complex line, and you take the cotangent bundle, or this is 2 copies of C plus C dual, and you have the standard symplectic pairing. So of course the coordinate ring of this is just polynomial algebra in two variables. Well, X, so this commutes, this is a commutative algebra, and you have a Poisson bracket on this. Here this would be a non-degenerate Poisson bracket. Right, and then you can do two things. Something that's well understood maybe is you go in this direction. This is what's called quantizing. So you go from a commutative algebra to a non-commutative algebra. And it's well known that the quantization of this coordinate ring of this T star of C that's called the Weil algebra. Yeah? And what you just do is, you, instead of saying, well, you quotient by this ideal x and y in this tensor algebra, you quotient by the ideal x, the commutator of xy minus 1, and the 1 is coming from the Poisson bracket. So you take the Poisson bracket and make it into an actual commutation relation. Or not commutation relation. So that's the Weil algebra, and sometimes, it's also the algebra when you have x and d by dx. So this is the typical commutation relation that's satisfied when you have the coordinate and then d by dx. Yeah? So this is the non-commutative algebra, and in a well-controlled sense, you can go to a classical limit and recover this commutative algebra. Then there's another thing you can do. So this is quantizing. You can go up in this direction, which people call chiralizing. And this is, you take this algebra and you make it into a differential algebra. So you add these formal differentials, dn. So now what will happen is, of course, in this easy case where there are no relations, you just have this polynomial algebra. So this is J infinity, this is called arc space or infinity jet scheme, but we don't need to really know what this is. In general, here it just means you're adding these formal derivatives. So now you just have a polynomial algebra in infinitely many variables, right? So this is called chiralizing or looping or something like this. And all the classical constructions of vertex algebras, you also do something like this, where you take finite dimensional Lie algebra and then you're adding these derivatives somehow. But this is now still a commutative thing, and then you can, and I'm not going to say how this works, but you can then do both, basically. And then you end up at a vertex algebra. And here the vertex algebra would be called, and this is a particular example, it would be called beta-gamma system or free bosons. So this is a very easy example of a vertex algebra that describes somehow these are, physicists like to call them free bosons of beta-gamma system. Okay, but right, so you can think of them, of vertex algebras as non-commutative and these chiralized versions of just these Poisson algebras. And now if you go backwards, if you start from a VOA, there's a well-defined, so these arrows are not really well-defined because this may not be unique, so this is tricky, but you can always go from here to here. You start with a vertex algebra, you can go back to this Poisson algebra, and that's what the associative variety is. Yeah? Okay, and it's of course you throw away a lot of information, but it just so happens we have this in some theorems, and sometimes it's just from experience that this associated variety, this thing down here, still knows a lot about the vertex algebra, about its representation theory, about the modularity of characters. Yeah. Okay. Right. So now we're just going to go through a couple of examples. So for A, are there any questions at this point? Maybe. Okay. So I'll give you, for A, this is the nice case. We've seen these we have seen these before. You take L, a positive definite lattice. And then there's a construction of a lattice vertex algebra. So you get from this a vertex algebra VL, lattice vertex algebra. Actually, there's a difference between vertex algebra and vertex operator algebra, but it doesn't matter for us, and it's just abbreviated by VOA. Okay, it's easier to say. So we have lattice VOAs, and here the characters. So what is the representations? So we have the irreducible modules are indexed by the discriminant group associated with this lattice. So they're of the form B alpha plus L, where alpha plus L is in L prime modulo L. And now you can probably already guess what the characters look like. Well, they will contain these theta series. The only thing is they have to have weight 0, so we have to divide by a power of eta, and that's it. So the characters here, the trace functions, are just of the form theta of alpha plus L of tau divided by eta to the rank of the lattice. Right. So this is now weight 0, and And in fact, these quotients behave a bit nicer than the theta theories themselves, namely they transform under SL to Z. You don't have to go to a metaplectic cover, so this cancels, right? So this is now, so they form collectively a vector valued modular form for SL to Z of weight 0. Okay, so this of course you know very well, and if you take a unimodular lattice, then you will only have one irreducible module. Yes.
Question about that. This would, the V alpha plus L and the V minus alpha plus L would be different modules despite having the same theta character.
Yeah. So exactly. So I mean, the dimension of the space can be smaller than the number of irreducible modules that you have, right? Yeah, so that can happen. Yeah. And in fact, there's a general thing that happens. Since you mentioned it, there is something called a dual module. So this is not just for lattice vertex algebras always. So you have a dual module, and here the dual module is exactly, you take minus alpha plus L, and it's always true that the dual module and the module have the same character. Yeah? Now, you can make them linearly independent by inserting some other function in here. This would be called one-point function. You can insert a field in here, and then it would become linearly independent, but if you just look at these characters, right. Now, there are vertex algebras where every module is dual to itself, and then the dimension could be the same, but in general, the dimension of the space will be smaller than the number of irreducibles. Yeah. Right. And yeah, if L is unimodular, and let's say of rank 24, well, then you just get the J function plus some constant. Yeah? So then you get the character of this lattice will be J of tau minus 744 plus some constant, which is the number of roots in the lattice. Yeah, so I mean, this you have to understand, which I didn't tell you, how this grading works on the lattice vertex algebra, but it turns out that this constant here, so you get the J function, and this constant depends on the number of roots of the, it's 24 plus the number of roots in the lattice. Right, and just a comment maybe on this monstrous moonshine. So people were trying to build a VOA where the trace function is exactly the J function without a constant term. And then with lattices, you will always have at least 24 here, so they knew somehow it couldn't be from a lattice VOA, so you had to make this a bit smaller, and then this led to the construction of the moonshine module. You start from the Leech lattice VOA, and you make some orbifold construction to make the space, make it in some sense equal. You end up with a J function and the whole monstrous moonshine business. Okay, this is just a side remark. Right, and there are many other examples of these nice rational VOAs where the characters, and they will often, even in other examples, will often have this form, some kind of theta series, some kind of summation, divided by something that's very combinatorial, like some eta. Yeah? It could be rescaled eta functions, and always in a way such that the weight comes to 0. So you look at these guys in these cases and you immediately see that the weight is 0, just because you know the components very well, typically. Yeah? Okay. Maybe that's the only one I want to write down. But it's usually of the form for the VOAs that we can construct by some kind of classical object like lattices or Lie algebras. You will always have some theta function divided by some etas. Okay. Then let's do an example for B.
L0 is always a non-negative grading, like the
So
power of Q would always be minus C over 24.
So on the vertex algebra, it's a part of the definition that L0 starts at 0. You have a vacuum, and then you have higher modes. On the modules, it can have negative weights, but there will be a lowest weight. Right. So these, I should have said that. So when you have these trace functions on the modules, on the irreducible modules, there will be always a lowest L0 eigenvalue. So you have Q series that have some lowest Q exponent. Yeah? And I should have also maybe mentioned that well, okay, this is implied here, right? So it factors through gamma n, so you have some denominator on the exponents in these cases, right? Let's say there are assumptions which make these exponents always positive, but in any case, because you're adjusting with the c minus, the central charge would be here equal to the rank of the lattice, and so typically you have negative q exponents coming from this correction, yeah, and it's just if you don't add this factor, of course, it will not be modular anymore. Okay, so for B. So for a long time, by the way, people believed that this weaker assumption of Lis, which really is just the assumption that the variety is a point, already implies rationality. This was a conjecture for 10 years. It's wrong. It is still believed that rationality implies that A implies B, but for this we have no counterexamples, but we don't have a proof of this. So I cheated a bit by ordering in this way. It's not really known, except strictly speaking, that A implies B. But for B, so for a long time we didn't have examples for B. So this was somehow, well, this came in maybe around 2000. People came up with these examples. And the most famous one is called the triplet VOA. Depends on the parameter P, where P is greater or equal to 2. And yeah, I'm just going to write down what the characters look like. So you have two P irreducible modules, which are ordinary modules. So they have the usual characters, and then you have P, but the space wouldn't close, and then you have P minus 1 of these pseudo traces. Let me write pseudo characters. Right. So what do these what do these look like? So what are the characters here? The characters here of the form, you have some theta function, but then you also have minus the derivative of a theta function. Right. So that you see already the weight is now mixed. Divided by some eta. Okay, so this is what they look like. And, well, together, they do span a 3p minus 1, so here they're linearly independent. They do span a 3p minus 1 dimensional SL to Z invariant space. Right, and these will have logarithms in them, yeah? I'm going to write down an example for p equals to 2 to make this very explicit. So for p equals to 2, let's say the character of the VOA itself, so that's the kind of the vacuum module or the adjoint module, looks like this. You have this is in terms of the standard theta 2. Here you see already. There would be, so here I'm setting the Jacobi variable to 1. It's just a Q character here, yeah? But this kind of hints at the fact that sometimes it makes sense to not have this equal to 1, but you need another operator that commutes with L0. Divided by 4 eta of Q plus eta Q squared over 2. Right, so this has weight 0 and this has weight 1. Well, I don't need to write this down. I think this is, here people see this immediately. And then if you now do the S transformation and you do the Peterson slash of weight 0 for S, right? It's always you have to do it for weight 0. Then you end up with theta 4 of 1 comma Q over 4 eta of Q. And then here, of course, because this has a different weight, this has weight 1, not weight 0, you end up with a logarithm. I tau over 2 times eta squared of Q. Right, and the explanation for this is that, well, okay, you do the S, this will be linear combination of something in these spaces, and some of these pseudo traces do have tau in them. So here they will have at most 1 power, tau to the power of 1. So that's the transformation behavior here. So this is a linear combination of the characters plus pseudo characters. Yeah. So that's typically what happens in these cases, and we actually don't have many examples of the. In most cases when x is a point, it somehow happens that it's already rational. So this is a bit of a rare thing. Well, okay. Right, so now, maybe personally I find C maybe the most interesting because it's something I'm working on at the moment. So I want to come to C. Where in terms of modularity, it's somewhat similar. I mean, you'll have infinitely many irreducible modules, but if you restrict to the ordinary ones that have characters, you probably still have the same behavior as here. Of course, then the question is how much does modularity, in A and B, modularity really tells you a lot, because you have the category here, as I mentioned, maybe is a modular tensor category, so it admits an action of SL to Z. And the S and the T matrix here are basically the same as the S matrix and T matrix here, you have to rescale a little bit, right? So then you have in these modular tensor categories, you have something called the Valinde formula. So if you know the S matrix, you know the fusion rules. That means you know the tensor products, basically, between the modules. And that's a very strong statement. Yeah? So studying modularity of characters can tell you a lot about the structure of this category here. Usually, you still have to prove some things, but it at least gives you a hint of what might be the correct statement to prove. Now, if you're in C now, unfortunately, the characters don't see a lot. They see only a small portion of the whole category, so you can't really expect such strong statements that we had before. That I'm telling you that you have been using in A and B. But yeah, nonetheless, it's still, of course, very interesting. I mean, so vertex algebra are part of this field in mathematical physics called conformal field theory, and the modularity of characters in conformal field theory is super important. I mean, this is before people even understood the categorical aspects, they knew that they had to write down a partition function or a kind of that's modular invariant, which is made up from the characters of these modules. And then for a long time they thought this is actually sufficient. And then people like Christoph Weigert, they said no. I mean, you have to also check consistency in a categorical sense. But nonetheless, the characters tell you a lot. Okay, so let's do C. So we had the beta-gamma system. So this is an example. I just write it down. I'm not going to write down the characters. So we have the beta-gamma system, which we had on the board, where the associated variety was T star of C, and that's a nice symplectic variety. Yeah? Okay, so then we have, here I want to just give you a couple of examples. Then we have affine VOAs, or maybe I skip this one. Right, I want to spend more time on those ones here. Something that people have been, including myself, have been studying in recent years are vertex algebras that have whose associated varieties are symplectic singularities. I had it in the title, which I erase now. The reason for this is that there is a kind of a program in mathematical physics to understand higher dimensional superconformal field theories by reducing them. So vertex algebras somehow are two-dimensional conformal field theories, and you can sometimes understand higher dimensional ones by reducing them to VOAs. And something that's very important in this context is this associated variety, which is conjectured to be always then a symplectic singularity in this context. And physicists can make many statements about these symplectic singularities. There's something called 3D mirror symmetry. Symplectic duality appears in this context. So there are many interesting geometric aspects. And that's why we try to kind of construct VOAs that have a given symplectic singularity. Okay, so let me just write down some examples. So VOAs with associated variety, nice symplectic singularities. Yeah, so typically these associated varieties will not be smooth. So it's very typical that they have singularities. So as example, as an example, we can look at the following one. That's the kind of the Sn singularity, which is you take the representation space of Sn, which is C to the n minus 1 copies of C, but you then always want to make it symplectic, so you take T star of C to the power of n minus 1. And you make this kind of diagonal action on this on C to the n minus 1 and the other copy by Sn. Right, so this is singular, and it has a nice resolution by the Hilbert scheme of n points in the plane. Now this is not quite correct. You have to remove. There's a kind of a copy of T star C here, so remove T star C. So this describes, this of course just describes n points in the plane where we don't care for the order. And the only thing you have to do is here, if you make this Hilbert scheme construction, you remove, this is kind of the center of gravity of these points, and this is not interesting. Okay, so but it's basically resolved, so this is a well-known symplectic resolution. Yeah? And let me also mention that this can be realized as a quiver variety, if someone has heard this before. So this can be the corresponding quiver here looks like this. Yeah, I'm just going to mention this. So this means you can get it as by Hamiltonian reduction of some symplectic vector space. Right. And if you go to n equals to 2, to make this very concrete, for n equals to 2, you end up with the nilpotent cone of SL2. So then this variety here is the nilpotent cone of SL2, which is resolved by the cotangent bundle of a projective line. Okay, right, so this is the Springer resolution then in this case. Right. Okay, and as I said, the motivation here to study such VOAs comes from mathematical physics, to try to understand higher dimensional conformal field theories, superconformal field theories, which are not mathematically axiomatized. So we have vertex algebras somehow are part of the axiomatization of two-dimensional conformal field theories, but for higher ones there's basically no mathematical, there's not really a developed mathematical approach, except for in special examples or certain aspects. Yeah, certain aspects are understood, but not the whole thing. And let me now come to one of my own results, together with Arakawa.
Well, symplectic variety, is this always birationally equivalent to projective space?
Is it rational, basically, or unirational?
I'm not sure if that's always the case. Yeah, I need to think about it. I mean, yeah. Yeah. Okay. Right. So what we did, we constructed a vertex operator algebra, V or W, I think you call it W, Sn, that has this associative variety with X is this M Sn, X of W Sn, M Sn, and right. So now I want to give you the characters, of course. Yeah? So what is the character here? So actually, this is a super algebra. And in principle, you also need to have vertex algebras that have somehow, fermionic degrees of freedom, so odd elements. And then instead of the characters, you're going to look at super characters. You'll include a -1 to the parity here. They have better modular behaviors than the characters. So it's a small detail. So here we have to look at the super character now. And the only thing that changes, it will not necessarily be invariant under SL2Z, but maybe under gamma 02. So that's a small change here. Okay, so the super character of this WSN, so this can be written in a very nice way. in terms of generalized divisor sums. So there's these, where they're called A and C, n minus 1 over 2 of q. And then the other one, you have eta, you have some eta stuff in the front, which is not really important. Q to the power of 1/2. So you see now you have half integral q exponents somehow. And that comes from the super character, because it's a super VOA. Q to the 4. And then you have some other thing, and I'll say in a second what these are. So these are, so this is for n odd. There's a kind of dichotomy here, n odd and n even. And these A and C are these, this goes back to 1920, McMahon generalized Q divisor sums. Okay. And these are examples, these are the easiest examples, I would say, of these Q multiple zeta values. Okay. And here they are nice quasi-modular forms of mixed weight. So these are quasi-modular for either SL to Z in one case, or for, no, I shouldn't write like this, or gamma upper 0, 2 of weight, and they have mixed weight of weights. The highest one is n minus 1, n minus 3, and then up to 1 or 2. We decrease by 2. Okay. So that's what you see here.
What do you mean by several weights? Like before, some of things with different weights?
They have mixed weight. Yeah, so there's, yeah. But somehow, I mean, and that also that happens also typically for Q multiple zeta values, that they have mixed weights. So here you have a very nice combinatorial representation of these things, but they're not. You will end up with something that's modular of mixed weight, or several weights. And as I explained, I hope I explained that this is a very natural thing that happens when you look at characters of VOAs.
Can you say something about the different depth? Like quasi-modular forms also have depth. Are the depth of the higher weights smaller than the depth of the lower weights?
Well, yeah, it has to be in a way that when you look at the modular transformations, you don't end up with negative Q log Q's exponents, right? The log Q that you get has to be positive in the other components.
Yeah.
So that's a consistency requirement on the depths that you have. Yeah? So for example, for n equals to 3, the character is square character here is very simple. It's 1 over 24, and it's 1 minus E2 of Q. Okay. So this is the normalized Eisenstein series of weight 2. Okay, so this is, yeah, so this is what it looks like, and people have worked them out in terms of Eisenstein series for up to, I mean, this is something you have to then do numerically.
This goes up to weight 0, so you end up at 1 or 0 in the weight, because you have here the constant 1.
Correct. Ah, yes, I forgot. Maybe, yeah, 0 or 1 then, yes. Correct, yes. Yeah, right. Okay. So now, what can we learn here from modularity? We can still learn a little bit. So of course we want to understand, so this is just the character of the VOA, and we don't at the moment really understand the relative representation category of this VOA. So we just constructed the vertex algebra, computed the character. It was fairly straightforward from the construction. Now what can modularity tell us about the representation theory? Well, we know at least one, so there is a short exact sequence. So what is the and you do it for n equals to 2. I mean, that's the easiest case. So for representation theory for n equals to 2, the way this vertex algebra is constructed is actually in a certain, there's a kind of certain short exact sequence. So this is the W here. and it can be embedded into beta gamma BC. So this beta gamma we've seen, this is a free field VOA, and these are free fermions. So this is a very kind of well-known vertex algebra, and well, we have a certain short exact sequence. But then we get for free, I mean, we have this free field embedding, this is injective, but then basically we get for free this quotient here of beta gamma BC by W, which is also a module. Just you know, you don't have to work for this. You get this M, and then you can look at, well, let's look at those characters. Now I have to say here the character, so these have infinite dimensional weight spaces. Here the character is only well defined in the Jacobi sense. That's, in this case, you can work this out. So here, the character here and here, this is, you need to look at Jacobi characters. I use this like just by meaning there's an additional operator that gives you then finite dimensional weight spaces if you look at the simultaneous eigenspaces. And right, so what does it look like here? So people have determined kind of the smallest representation of SL2Z in which this can sit. So you have the character, you have the supercharacter of the VOA, W or WSN. And then you see already here there will be something logarithmic. So you have, let's call this F log. And I said there's a Z and tau here. And if you work this out, these are really, I mean, if you can work this out in terms of, if you include this variable Z, then you have nice theta, Jacobi theta series appearing. Or maybe derivatives of them. Right, so you have something logarithmic. You can compute what it looks like, but we don't at the moment know what kind of module it corresponds to. So here there's kind of a question mark, yeah? But we know it must exist if we assume that there is some kind of modularity on the characters. And then there's so this is two-dimensional. And then there's a one-dimensional part which comes from this M. So M, the character of M is already closed under module transformations. And the difference here is now that this is well defined under Z goes to 0. So here Z goes to 0 is okay, but here you cannot do Z goes to 0. Yeah? Okay. Yeah. So you have if you want to look at ordinary characters, we have a two-dimensional representation of SL to Z. But we know from other considerations that there are going to be many more modules that just don't admit characters in this sense.
So you cannot, it means it has a pole at Z equals 0 or something?
Yeah, this will, exactly. So this this will, yeah, yes. So which means that the ordinary character wouldn't be well defined, right? If you don't include this additional operator. Right, so what I mean, I can write it down, right? So you have, so what you do here is you take the trace over Q to the L0 minus C over 24. Then we also have the minus 1 to the parity, because it's a super character, and then there will be Z to H0, and H0 is just, it comes from a certain representation of SL2 in this vertex algebra. And that helps you a little bit with getting finite dimensional.
The exponent of Z.
Hmm?
Z or the exponent?
Yeah, Z, right. Z is the one, if I, yeah, e to the 2 pi I Z H0, yeah. Right. Okay, let's see, yeah. So then as I said, so what we expect here is you again, like in B, you have your characters. Here it's just one because this VOA doesn't have many ordinary modules, probably it just has one itself. Then there will be some kind of logarithmic module, let's say, which we don't know yet what it is. And then this space is closed again under SL2Z. At least here we need to add one more component to make this close. Right. So now, I haven't talked about D yet, so I'll just make one example for D because it's also kind of nice. Right, and I mean for looking at maybe going back to Charles' question, just very briefly. So this, of course, that's no problem. The modular transformation here. So if I take E2 and do the transformation under the S under for some matrix under weight 0, yeah, then of course what you end up with, you have C tau plus D squared E2 plus 12 over 2 pi I c times c tau plus c. Yeah, so it's important. So you end up with positive exponents of, positive powers of log q, and that's what you want. So that's fine here. Okay, let me do one example for the last one, or maybe two if I have time. Yeah. So we have the Heisenberg VOA, which is a very simple VOA, but it's maybe the first VOA that we would define, but unfortunately it doesn't have, it's in this category D. So you have the Heisenberg VOA. And the associated variety here is just, so the Heisenberg VOA is built from an abelian Lie algebra. And I take a one-dimensional abelian Lie algebra. So it's by an affinization of an abelian Lie algebra, let's say H. And the problem is now that you want to have some kind of symplectic form here, but here it's 0. So the natural symplectic form you have on such an abelian Lie algebra is just 0. So it's degenerate. If you had a simple Lie algebra, this would have a somewhat better behaved symplectic form on it. Right. Anyway, so what's the space here? It's just if I take a 1, let's say, do I want this in rank 1 or I guess I want to do it in rank 1. So this is just C. So the associated variety is just C, and this has a degenerate. I mean, you cannot put a symplectic form anyway because it's one-dimensional. So this has a degenerate symplectic 0. This is the symplectic form here is 0 symplectic form, or Poisson bracket. Okay, so this is, in that sense, very badly behaved, and I want to call this Heisenberg VOA pi 0, and it has a continuum of modules, of irreducible modules. Continuum of irreducible modules. They're called Fock modules, and they're just indexed by lambda, where lambda is, you could take any complex number, but let's restrict to real numbers. Otherwise, my argument is not going to work in a second. And what do the characters look like? They're just of the form some q to some, well, it's lambda squared over 2 divided by eta of q. Okay, so you have eta, which is okay, but then here you just have one single q exponent with some power. So this is of course not modular. But this still satisfies modularity in a continuum sense. So let me just write down what you get. So if you take the character of pi lambda of -1 over tau, which is just you take q to the lambda squared halves over eta of q. Now we apply the S transformation of weight 0. No, I don't want to write like this. Then maybe up to some factor. This is, you can write as an integral now over some S kernel. Yeah, so there is not going to be an S matrix, but there will be an S kernel, and it's just going to be a Fourier transform. 2 pi I lambda times mu. So this maybe you want to call S of lambda comma mu times q to the mu squared halves over eta of q d mu, right? So, but I have to say this we only understand well in this one and another example. Yeah, so here you have many irreducible modules. They have well-defined characters, and they are still modular of weight 0 in this continuum sense. Here you just take the usual Lebesgue measure on R. Of course, there's nothing really that tells you why this is the right measure to take, but here it just works. Yeah, it works like this. So you can still make sense of this property that the space of characters should be closed under the action of S to Z, but now it's in this sense, right? Okay.
The sum over lambda integers will just get theta over eta. I don't know if this operation
so
give you something modular directly.
Yeah, but but then you're not looking at all the modules. But I come to this in a second. What what you want to do, you want to take the sum over, let's say, integer values of lambda, but then you're building a lattice vertex algebra. Because if you take, so let me write this down, it's a very good observation, of course, you make this modular by summing over some lambda being integers. But what happens if you sum over these Fock modules? You're building a lattice vertex algebra, which has a modular character. So, and that was the last point I was going to talk about anyway, and I don't have much time, so I'll just do it in this one particular example maybe. Yeah, this would be chapter 3 now, but this is like vertex algebra extensions. Vertex algebra extensions. And somehow, if you have vertex algebras in this last category, or maybe C, that are not very nice, you can extend them to bigger VOAs. And if you go to a bigger VOA, then they become simpler. And this means you're summing characters in some sense. And the easiest example of this is you have the Heisenberg, and this is the first example. You take the Heisenberg VOA, let's say, actually I take, in general, k copies of this, because I want, and then you're summing, you're extending now to a lattice VOA. And what does the lattice VOA look like? Well, it looks like a direct sum, alpha in the lattice, pi alpha of this, rank k Heisenberg. Yeah? So this is how you actually construct a lattice VOA. I didn't tell you before, but that's how you construct a lattice VOA. And then you see, of course, that you just have to sum the characters, and so then the character becomes, on the top you get a theta series, and this becomes modular. Yeah? Right. So. So I can write this down. So the character then of the lattice VOA, the character of this lattice VOA is then the sum alpha in L of the character of these pi lambdas. And this has then much better modular properties than the character of the original one that you started with. And this
alpha, sum over alpha of pi. Alpha.
Yeah. Thank you. And that is a general theme, that when you have a VOA that's maybe not so nice, sometimes you can go to, you can extend it to a bigger VOA that has nicer properties. And I just want to end with a second example that's related to the symplectic singularity business. And I'm just going to sketch it. So we have, it's a different symplectic singularity. We take the minimally potent orbit closure of SLN. This is some symplectic singularity, which would be resolved by T star of P to the n-1. And we can build a VOA that has this symplectic singularity. For n equals to 2, it's the same one as there, but in general it's different. And what do the characters look like? Well, right, so here, the VOA that has this symplectic singularity has, again, quasi-modular characters, but there is, so what is the VOA here? So the VOA that has this is an affine VOA at some level, at level 1 actually, for the Lie algebra PSL NN. Just to make this specific. That's it. That's a vertex algebra that has this symplectic singularity. But this contains, so this is relatively nice, but this contains, because you can decompose this Lie algebra in some sense in 2 copies of SLN. So this contains a vertex algebra for SLN at level 1 and one for at level -1. I didn't explain what level means, but I just have to write this down now in this form. And this is one of those cases that Katrin Kringmann and Anton Milas have studied, where you get mock modular forms. So here you have mock modular. Here, this is actually, because it's level 1, this is just the lattice VOA of the A n-1 lattice. So this is a very nice VOA that has just, as we've seen, theta series as characters. And now, by some kind of miracle in some sense, when you add all of these up, we end up with this VOA And we know then that these are just quasi-modular forms. So here you have this behavior that
Can you
something
repeat what's the level of the original VOA?
1.
This is a 1 here. Okay.
Yeah, it's a 1. Yes. Right. So there's so people have studied this VOA, the one at level -1, and it's kind of nasty. And if you look at the associated variety, then it will be some sheet that contains this. So it's a kind of worse geometric structure. But by embedding this, well, you have to add something here. You have to add this SLN at level 1, which is a very nice one. By embedding this, and then here you have this is an infinite extension. So this is infinite, yeah? Infinite index extension. You end up with a VOA that's much better behaved. So this here is A in the category A. This would be in D, and this would be then in C. Okay, and that's somehow where I want to end this talk. And this is not something that's well developed, but it's kind of when I was preparing a talk for this conference, I was thinking, what is a story that I can tell? The story that I can tell is that vertex algebra extensions are something we have well under control. And it sometimes leads to this behavior that you start with characters that are not super nice, but somehow by summing them up, you end up with characters that are quite nice. Whether you can learn something about this, that I don't know. I mean, this is just, we know it in a few examples, but anyway, that's something you can observe. Okay, here I stop.